let's talk about, so simple harmonic motion, we can apply this to tons of systems. So this problem might look a little familiar to you guys. It's, I ripped it out of the midterm 2 from 2012 that you guys used to practice on. So if we look at a satellite going around a much larger mass in orbit, we can write that the effective potential for this situation is given by L squared, which is the angular momentum of the object, over 2mr squared minus the gravitational potential energy. So let's see what we can do to describe the system using our new tools. First, I want you guys to think about, what does this potential look like? Like, let's take a shot at it. Let's sketch this out. Get out some paper. Let's try to figure out, without any calculator, no Wolfram Alpha, no Mathematica, let's just try to figure out essentially what this thing is going to look like. I'll give you a hint. Think about the limits when R gets really, really tiny, and the limits when R gets really, really big. Okay, so when R is really, really tiny, which of these two terms up here, the 1 over R squared term or the 1 over R term, which one is going to dominate? The left one? Why? Well, because it's 1 over R squared, right? And so if R is a really, really tiny number, let's say R is 10 to the minus, let's say even just 10 to the minus 6 meters. Okay, on the left you have something that's 1 over 10 to the minus 6. That sounds like flip it over 10 to the 12. But the other one is just 1 over 10 to the minus 6, which is flip it over 10 to the 6. 10 to the 12th is a lot bigger than 10 to the 6, so that one's going to dominate. So what does that thing do? It goes to infinity, and it looks like that's a positive term, so it's going to positive infinity over here. Okay, now what about when R gets really, really big? Which term's going to dominate now? The negative one, because the exact argument we just gave, let's write that. Okay, so now the right term is going to dominate when R gets really, really big. It's going to go to what? 0, okay. Now, where is it coming from? Is it coming from positive or from negative? It's negative. Okay, so we have something approaching 0 from the negative. So now, if I need to connect those two together, I'm going to end up with something that looks like this. All right. So now we have a potential well. Okay, awesome. Thank you. All right. So now I want to ask you this question. It's not a quick question. Oops. Okay. Well, first, where is equilibrium going to be? The bottom. So I think it's helpful when looking at these potential energy functions to imagine that we place a little marble in there and think about what it's going to do. So if I place a marble right here, what's it going to do? It's going to stay there. So that's a nice stable equilibrium. So that is what I'm going to call R naught. That's my equilibrium point. Okay, awesome. So now, if you have this satellite in orbit and it's at your equilibrium point, what is that orbit going to look like? Well, if it's right here, if there's your little marble, it doesn't really want to move from there, right? It's going to stay at this constant radius. So that's, and this orbit with a constant radius, that's just circular, right? Okay. So, at equilibrium, sorry, I gave away the answer. We can say that the derivative of this guy is equal to 0, and that's how we can find where the equilibrium point is. So if we take the derivative of this function, we get something that looks like this. And if we say that at the minimum, we know that the potential energy derivative has to equal 0. for this thing inside the parentheses to equal 0. So therefore we have at R naught, we have minus L squared over M plus G M and R naught equals 0. So then we get R naught is equal to L squared over G and M squared. Okay. All right, is that what you guys got? Yeah. Awesome. All right, so now we've fully been able to describe what this circular orbit looks like. Well, with what we've been given. Okay. But now let's imagine you have this circular orbit, and let's say something moves by the satellite, and it perturbs its orbit a little bit. So what's going to happen? So we take it slightly, so let's go back to our marble. Let's take our marble and let's perturb it. Let's move it to one side and position a little bit. If I put my marble over here, what is this thing going to do? It's going to go back and forth, right? It's undergoing oscillations. And so that's essentially what our planet is going to do. It's orbiting. Its radius is going to get bigger and smaller, and it's going to oscillate around the stable radius R naught, which is for circular orbits. Okay. So now that's kind of a complicated potential energy function. So far, everything we've talked about has been nice and simple. We've been doing a lot of talk about springs. So if we can look at this potential energy function, remember at the very end of the lecture last time, we said you can take a really ugly potential energy function, but if it has a potential well, some sort of little wrapping right here, if we zoom in on it really close, what can we make it look like? A parabola, right? Okay, so if we can zoom in just on that section, we can make it look like a parabola. And a parabola is a potential energy function that goes as x squared, much like a spring. And then we know exactly how the motion of the spring goes. So let's see if we can make this guy look like that.